Hey everybody, this is Austin Hoggett here to give you another lecture from our OpenStax Intermediate Algebra textbook. Today we're going to start in Chapter 3, talking about graphing linear equations and looking at a few different functions later on in the chapter. For now, let's get started on our discussion here in 3.1 on graphing linear equations in two variables. We'll talk today about plotting points in the rectangular coordinate system, giving a sort of definition for the coordinate plane itself. And the rest of these topics really deal with the same thing. How do we graph different versions of the question on these variations of linear equations? Starting with plotting points in a rectangular coordinate system, we see here an example of what the coordinate plane might look like. And we discuss particular points inside the plane in terms of these ordered pairs. So these xy coordinates give us a location within the plane, and they're always in reference to a starting position known as the origin. So if you can think of, let's say, the x and y axes here as perpendicularly laid number lines for two different measurements that have some relationship that we can describe in terms of some linear equation, right? Movement within this plane can be described in terms of movement from the origin either left or right on that x-axis, and then a movement up or down on the y. Another characteristic of the coordinate plane is that we sort of divide it into these four quadrants, and they go in a counterclockwise manner, starting from the top right here. And these quadrants are distinguishable by the particular signs used for movement within those quadrants. So for instance, the first quadrant, you'll notice, is always going to have positive values for deciphering, in particular points. So if I place a individual point within that plane, I can, for instance, decide where it is based solely on, let's say, the xy values chosen. So for example here, again, we speak to how to get at a particular place within the field by movement with respect to the origin. In our first example here in part A, it looks like our x coordinate is -5. So from the origin point there at 0, 0, we would move 5 units to the left on our x-axis and then 4 units up on the y-axis, landing us right around here. So we can label this as our point. In some formats, you might be asked the question the other way around. I give you a point labeled as A or some other name, and you give me back the x and y values that it takes to get there. So for instance, if I plot a point here, and we just call this something like, this is F, right? The particular location that describes that point would be 4 units of movement in the right direction along the x-axis, and then 2 movements forward in the y direction. So we could say 4, 2 would be a representative coordinate pair to represent that point. Now the individual point along the coordinate plane may or may not correspond to some particular solution of a linear equation. Now the linear equation has typically this form: ax plus by is equal to c. There's another form that we'll see coming up later in the chapter called the slope-intercept form that deviates from this slightly. And we'll talk about how to actually convert back and forth between those two and when that's convenient. But the standard form of the equation here, as it's written, indicates that we have two variables inside this equation. And one thing we know about solving for variables, or should recognize, is that we need at least as many equations as unknown variables if we're going to solve for this. So for instance, if I give you the equation 2x plus 3y is equal to 10, and I wanted to know what the solution to this equation is, algebraically speaking, there's not much we can do to solve it. So we talk about in this chapter actually how are the methods, or at least what are the methods available to us to solve something like this. And our solutions for an equation such as this, instead of, as before, if we had an equation very simply 2x equals 10, I would say, well, x has to equal 5 because 2 times 5 gives me 10. And that creates a solution. But with a second variable in place now, I have to arbitrarily choose values for one, substitute in that value, and then solve for the other to ever get at least a solution started. And that becomes very tedious because what you'll notice after a while is that there's actually lots of different values that can substitute in for either x or y to create a solution. So graphing these linear equations is actually an efficient way to understand all the different solutions to these types of equations. And if you think about it, they're really just lists of x and y values. And so each of these ordered pairs, while on a coordinate plane may only represent a point, strung together, they are something akin to, let's say, the solution to a very simple equation like x is greater than 2. So on the number line, I could imagine, here's 2. If x is supposed to be greater than 2, there's actually a large range of values that make that statement true. Extending that same premise into the coordinate plane, we can look at a graphic of all the solutions, as you see here on the right. So my linear equation here is in not quite the standard form, as you see written in the left, but the slope-intercept form, as it's come to known, because it demonstrates to us the slope by virtue of the coefficient on the x term and the intercept, this constant term added to the end. We'll talk more about that in a later section from this chapter. But the visual here is simple enough to understand. This solid line is actually made up of individual xy values, xy components that make that equation true. So we can answer the question here on the left. Are the following points on the line? Well, we've got to plot them. Looking at part A, it says to plot the point 0, -3. So I move 0 units left or right on the x axis and then down 3 units along the y, which puts me right here at the cross of the y-axis. We actually refer to this point as something special called the y-intercept. The y-intercept is just where the graphic itself, the linear equation, crosses the y-axis. And what you might notice is that the point that I called out earlier is this constant term, -3 at the end, is what represents the y-intercept. And so there's a correlation there, again, that we'll describe later. So I could say for 0, -3, that's definitely on the line. Something like 3, 3 would also land me up here on the line. 2, -3 would be somewhere like this, so clearly not on the line, and therefore we could say it's not a solution to our equation, meaning substitution for x equals 2 and y equals -3 would cause me to have some false statement after simplifying. And the last one here, -1, -5, also puts us on the line way down here at the bottom. Something like this. So we can graph a linear equation using individual xy values, but we have to infer a lot in order not to drive ourselves crazy solving this. What I mentioned earlier is that equations like these can actually have lots of different answers. So a graphic as a visual aid to understand what all these solutions are is helpful, but how do you generate that graphic in the first place? Well, the nice thing about a linear equation is that we know what it should look like. Linear implies that it's going to be a straight line. And so from our geometry, we can understand that to create a straight line, we really can only, we really only need 2 or 3 points at minimum to create the inferred line that is the solution representing all the values that make that equation true. So here's how we graph that linear equation by plotting the points. Simply select values for the x or y component, make that substitution, and then solve for the remaining variable. Those two graphics, or those two x and y values together can be plotted in your graphic. And after you've defined enough of those ordered pairs, you can then infer the linear equation, the linear line. So our equation here is y equals 2x plus 1, and we're asked to graph our plotting point. So again, I'm just going to start by creating a list of x values. So let's make it simple. I want to substitute in these values for x into the equation. So I'm going to make them really simple, like 0, 1, and 2. Right? So for x equals 0, if I plug that into my equation, I get y is equal to 2 times 0 plus 1. Well, 2 times 0 disappears, and we get plus 1, so y equals 1 would be what the expression simplifies to be. And so I can put that into my list. Repeating this process for the other two, I get 2 times 1 is 2, plus 1 gives me 3. And when I substitute in x equals 2, I get 2 times 2 is 4, plus 1 is 5. So now I've created a list of x, y ordered pairs. Let's plot each of those individually. So 0, 1 would mean I move left or right 0 units along the x-axis, and then 1 unit up on the y-axis. So that will be right here. 1, 3 puts me somewhere like here, and 2, 5 puts me here. So notice that, again, there's a symmetry between these particular points that we've created. And I will mention again here the form of this particular equation. It's not in the standard form ax plus by is equal to c, but this in other form entirely, the slope-intercept form, where the b term is where this crosses the y-axis. And you'll notice that our very first point that we've plotted is exactly that y-intercept. And the slope, m, the coefficient on our x term, can be described in terms of something called the rise over run. It's basically an analogy for steepness of the line, right? So from moving to one point to another, I could move up 2 units and over 1 unit, right? Recognizing that 2 over 1 makes the ratio that represents the rise over the run of my line. And so after I see a few of these patterns, I can just sort of understand that, or infer, my line should look something like this. Right? And so the arrows here indicate that it extends infinitely in either direction. So we knew that this was a linear equation, so we can infer that straight line from just selecting 2 or 3 candidates to substitute into the equation, and there we have our plot. Now there's a couple of particular examples that we'll talk about here that are sort of oddities of the two forms that I mentioned here. So we've already mentioned that ax plus by equals c form, which is the standard form, and then the other y equals mx plus b. These vertical and horizontal lines take on a slightly different format. The vertical line is the graph of an equation that has the form x equals to a constant. And the line passes through the x-axis at whatever that constant happens to be. And the other component of that is going to be 0, right? That's the x-intercept. And so in contrast, we could see that y equals some constant would take on the form of some horizontal line, right? Now, because of these equations, the x equals a constant or y equals a constant, we can still plot using the same tabulation method that we used a moment ago, only this time, because one of our variables is always equal to a constant, the table is not very interesting. So for example, here I'm asked to plot the equation x equals -3. Well, if x equals a constant, no matter what value I choose for y, well, the outcome should always have x equals -3. In fact, there's no substituting to be had here. Arbitrarily, any value I choose for y, the corresponding x component has got to be constant, so -3. And if you build enough of these, you'll see that after 2 or 3 points, I can infer that the straight line is nice and vertical right where that x equals 3 x value is. Similarly, for something like y equals 4, I can build a tab on the left here that shows y equals some constant term. So no matter what value of x I choose, the y component will always be at 4. And again, plotting 2 or 3 of these points, we can infer a nice horizontal line at whatever that constant value is. All right.